Hello everyone. Today I am Rishabh Bhardwaj, Assistant Professor from Mechanical Department, taking the lecture of the subject named Applied Thermodynamics. Let's start with this lecture, and today in this lecture we will learn about the gas vapor cycle. In the gas vapor cycle, we will study about Otto cycle and the diesel cycle and the various comparison between the Otto cycle and the diesel cycle. Let's start with the initially with the Otto cycle. The Otto cycle is basically based on the Rankine cycle, by which the air and the fuel ratio mixture, or we can say that air fuel mixture is taken as a medium or as a working fluid, by which we will get 1 to 2 process as reverse adiabatic compression process, and 2 to 3, that is a heat addition process where QH is going inside the cycle. That shows that heat is entering in the system. Then 3 to 4 process is reverse adiabatic expansion. Then the fourth process is rejection of heat at a constant volume. Here the QL is heat of the at lower temperature is releasing. The 2 to 3 process is isochoric process, as it has a constant volume, and 4 to 1 is also a isochoric process as the volumes remain constant at this process. The Otto cycle is a basic phenomena by which our petrol, or we can say SI engine, has performed. Its efficiency is up to 1 minus 1 by R gamma minus 1, where R is the compression ratio and gamma is the adiabatic constant, where for the air the gamma value is 1.4. An Otto cycle is an idealized thermodynamic cycle that describes the functioning of a typical spark ignition piston engine. It is the thermodynamic cycle most commonly found in automobiles engine. The Otto cycle is a description of what happened to a mass of gas as it subjected to change of pressure, temperature, volume, addition of heat and removal of heat. The mass of gas that is subjected to those changes it's called the system. The system in the case is defined to be a fluid that can be the gas within the cylinder. By describing the changes that takes place within the system is also described in inverse. The system effect on the environment in the case of Otto cycle. The effect will be to produce enough network done from the system so as to propel an automobile and occupants in the environment. The Otto cycle is constructed from two top and bottom of the loop, a pair of quasi-parallel and isentropic process, that are the frictionless and the reversible adiabatic process. And the left and the right side of the loop, a pair of parallel isochoric process that has a constant volume. The isentropic process of compression or expansion implies that there will be no inefficiency and there will be no heat transfer of heat into or out of the system during that process. The cylinder and the piston are assumed to be impermeable to heat during that time. Work is performed on the system during the lower isentropic compression process. The heat flows into the Otto cycle through the left pressurizing process and some of its flow back out through the right depressurizing process. The summation of the work added to the system plus the heat added minus the rate of removed yet the net mechanical work generated by the system. In this process 1 to 2 and the piston does not work on the gas, and in 3 to 4 the gas does not work on the piston. During the isentropic compression and expansion process respectively, processes 2 to 3 and 4 to 1 are isentropic processes. The heat is transferred into the system from 2 to 3 and out of the system from 4 to 1. But no work is done on the system or extracted from the system during these processes. No work is done during an isochoric process. It's just because the addition or the removal of work from system requires the movement of the boundary of the system requires the movement of the boundaries of the system, and as a result of the cylinder volume does not change and no shaft work is added to or removed from the system. The four different equations are used to describe those four processes. A simplification is made by assuming the changes by the kinetic and the potential energy that takes place or can be neglected, and then applying the first law of thermodynamics to the mass as it changes the state of characteristics by the gas temperature, pressure and the volume. During a complete cycle, the gas returns to its original state of temperature, pressure and volume. Hence, the net internal energy changes to the system is zero. As a result, the energy added to the system must be offset by energy that leaves the system. In the analysis of thermodynamic system, the convention is to account energy that enters the system as the positive and the energy that leaves in the system is accounted as negative. Let's move to the next topic, that is diesel cycle. In diesel cycle there is a complete revolution takes place. Just changes is that 1 to 2 process is the reverse adiabatic compression, and 2 to 3 is a heat addition at a constant pressure. 3 to 4 is reversible adiabatic expansion, and 4 to 1 is rejection of heat at the constant volume. At the point 3 there is a cut-off point by which we are able to change the complete pressure at that point. Its efficiency is about 1 minus 1 by r raised to the power gamma minus 1 into alpha raised to the power gamma minus 1 by gamma in the bracket of alpha minus 1. Here alpha is the cutoff point here. Let's further discuss about diesel cycle. The diesel cycle is also known as the constant pressure cycle. As there is two processes are at the isobaric process. The diesel cycle is a combination or combustion process of a reciprocating internal combustion engine. In this, the fuel is ignited by heat generated during the compression of air in the combustion chamber, into which the fuel is then injected. This is in contrast to igniting the fuel air mixture with a spark plug, as in the Otto cycle engine. The diesel engine are used in aircrafts, automobile, power generation, diesel electric locomotive, and both surface ship and submarines. The diesel cycle is assumed to have constant pressure during the initial part of the combination phase, that is the volume 2 to volume 3. This is an idealized mathematical model, and real physical diesels do have an increase in pressure during this period, but it is less pronounced than in the Otto cycle. In contrast, the idealized Otto cycle of gasoline engine approximate a constant volume during the phase. The diesel engine is a heat engine. It converts heat into work. During the bottom isentropic process, energy is transferred into the system in the form of work that will be shown as the W in. But the definition, no energy is transferred into or out of the system in the form of heat. During the constant pressure processes, energy enters the system as Q in. During the top isentropic processes, energy is transferred out of the system in the form of work out, but no energy is transferred into or out of the system in the form of heat. During the constant volume, the process, some energies flows out of the system as heat through the right depressurizing process, that is Q out. The work that leaves the system is equal to the work that enter the system plus the difference between the heat added to the system and the heat that leaves the system, or we can say in the other words that net gain of work is equal to the difference between the heat added to the system and the heat that leaves the system. The net work done will be counted as the Q in minus Q out. The net work produced is also represented by the area enclosed by the cycle on the PV diagram. The net work done is produced per cycle and is also called the useful work, as it can be turned to useful type of energy and propel a vehicle or produce electrical energy. The summation of many such cycles per unit of time is called the developed power. The W out is also called the gross work, some of which is out in the next cycle of the engine to compress the next charge of cycle. Here we have the maximum thermal efficiency of diesel cycle is depending upon the compression ratio and the cut-off ratio. As from the formula, we can that the alpha is the cutoff ratio, that is volume 3 by volume 2. R is the compression ratio of volume 1 and volume 2, and gamma is the specific heat by Cp by Cv, and the which have the value 1.4 for the air. Next we have the comparison between the Otto cycle and the diesel cycle. The following are the important variable factors which is used for the comparison of this cycle. First, basis on the compression ratio. Second, on the basis of maximum pressure. Then heat supplied and rejected, and finally with the work done. As we will discuss first about the compression ratio, the Otto and the diesel cycle have different compression ratio and as well as the heat variation. The process 1 to 2 represents isentropic process for the same heat supplied if the compression ratio is same. The Otto cycle result in maximum pressure and temperature for the diesel cycle. These values are least while the other cycles have the value for the pressure and the temperature lies between them. It is the evidence that the heat rejected by Otto cycle is minimum and for the diesel cycle is maximum. Since work done equal to the difference of heat supplied and heat rejected, and the efficiency is the ratio of work done to the heat supplied. It follows that for the same compression ratio and heat supplied, the Otto cycle has the maximum efficiency and the diesel cycle has a least efficiency. Next we have maximum pressure and a temperature, or we can say that heat supplied. For the second portion we have a compression ratio, heat supplied, and then we have for constant maximum pressure and supplied. And it is observed that a diesel cycle would be more than Otto cycle for the same maximum pressure and temperature achieved during the cycle. The efficiency is of diesel cycle is greater than the Otto cycle. It should be noted that in case the compression ratio for diesel has to be more than Otto cycle, as the compression ratio for the Otto cycle is 9 to 14 and the compression ratio for diesel cycle that is 16 to 20. For the maximum pressure, the pressure 3 and pressure in the both the cycle are same, and the heat rejected by diesel cycle represent that the Otto cycle is having least maximum pressure. For the next we have for the same maximum pressure and temperature. In this we can easily see from the figure that from 1 to 2 the whole process is same, while the 1 to 3 is the is for the Otto cycle, by which it shows that the value for Otto cycle and 1 to 2 dash represents the cycle of diesel cycle, where 2 to 3 is the process for compression for the heat addition. Here the 2 to 3 process is for heat addition. The main and the major difference between the Otto cycle and the diesel cycle, as the compression is taken to 2 to 3 in the Otto cycle at a constant volume, and the heat addition at 2 to 3 in the diesel cycle, where the process is constant pressure. The major difference between that is the heat addition, the time of heat added to the system, and both heat rejection is same at same process, that is 4 to 1. This is the similarity of Otto cycle and the diesel cycle. As per the as per my knowledge and as per the design of the cycle, the diesel cycle has maximum or greater efficiency as compared to the Otto cycle. It's about kind of double the efficiency of diesel cycle, and the life cycle is more in Otto cycle as compared to the diesel cycle. And thank you for watching this video and stay tuned. Thank you.